Let's begin with a lingering issue in physics. We inhabit two distinct worlds that are simultaneously real. On one side, there's the vast universe, described by general relativity. Here, gravity isn't merely a force, it results from the curvature of space and time due to mass and energy. Planets orbit stars, galaxies interact, and everything can be predicted with remarkable precision. At this scale, the universe appears orderly, stable, and quantifiable. Yet, on the other side is the quantum realm, where the rules shift drastically. Particles like electrons and photons lack definite positions until measured. They don't behave like ordinary objects, but rather follow probabilities, making uncertainty a fundamental part of their nature. The real problem is not just their differences but that both theories are true yet do not merge. General relativity hardly considers quantum effects, while quantum mechanics typically disregards gravity. It's as if the universe speaks two languages that fail to translate. This raises deeper questions. Is gravity indeed irrelevant at the quantum level, or have we just not perceived its role? At microscopic scales, gravity is exceedingly weak. If two small objects are placed in a vacuum, they won't significantly attract each other as planets do. Their masses are too small to create a considerable gravitational impact, making gravity seem absent in the quantum domain. However, gravitational effects are never truly gone. Every particle with mass contributes to the curvature of spacetime, however minuscule. The issue lies not in the existence of gravity but in our ability to detect it. Our instruments aren't sensitive enough to capture these minute effects. Here, we begin to uncover the gaps in our understanding. In the quantum world, uncertainty is often viewed as a limiting factor. We accept that position and momentum cannot be simultaneously known with certainty. Yet another possibility, seldom addressed, looms. What if this uncertainty isn't chaos but indicates a deeper pattern yet unseen? This implies a more fundamental structure governs particle behavior, potentially including how gravity operates at such scales. It doesn't mean the laws of physics are broken, rather, we may not have attained the level of understanding to perceive their order. This leads us into the next idea, one that transforms our conception of space itself. Traditionally, space is viewed as mere emptiness, a container for events to unfold. In this framework, however, space becomes an active entity. It's not just a backdrop, it possesses physical properties that influence what exists within it. If mass can warp space, one must ask, does space itself possess characteristics that can generate gravitational effects? This notion opens the door to the possibility that gravity originates not only from objects like stars and planets but also from the very structure of space. We've long recognized two mysterious concepts in cosmology: dark matter and dark energy. Both are invisible and undetectable directly, yet their effects are palpable. Galaxies rotate faster than expected, and the universe expands at an accelerating rate that ordinary matter cannot solely explain. One possibility is that what we consider empty space is far from vacant. Space might harbor energy distributions or internal structures causing subtle yet extensive gravitational effects. These effects may not dominate at small scales but become significant at galactic or even cosmic scales. In other words, two layers of gravity may function concurrently. First is the gravity from mass, the kind we know and can measure, a local and potent force that dictates orbits and interactions between physical objects. The second is gravity arising from space itself, unseen and indirectly detected, potentially crucial for maintaining the universe's large-scale structure. Dubbed internal space gravity, it differs from external gravity, which is local and strong. Internal space gravity influences the distribution and stability of systems on a grand scale. We can observe its implications in galactic structures. Stars are affected not only by surrounding mass but also by the background of space they inhabit, which may play a role we have long overlooked. This transforms our perception of reality. It's no longer merely about objects influencing space, it's also about space influencing objects. If space possesses gravitational properties, the boundary between empty and full begins to blur. What we consider void may be the most active foundation of the universe's entire structure. If this is indeed the case, the next question shifts from whether gravity exists in the quantum domain to how the gravity of space itself interacts with reality at the smallest scales. This theory begins to unlock doors to far greater mysteries.